This is William Tomos Edwards from Bright Studies, and I saw this integral the other day posted by Integrals for You on Instagram. Now I want to show you how I solve it. So at first, when I start looking at this integral, I think to myself, okay, this looks kind of like something where we could use a trig identity, an inverse trig identity, that is. This looks kind of like something where we've got the derivative of arctan. This looks kind of like something where we can do trigonometric substitution, but obviously not quite. So I start thinking to myself, wouldn't it be nice if that was x squared instead of x to the fourth power? Then it looks like almost we can start thinking about trig identities, trigonometric substitution, and all that great stuff. Okay, fair enough. So, then I look at it and say, well, we've got x right here. Imagine that was 2x, the derivative of x squared. Then we can, basically get rid of an x squared. We can bring that x to the fourth down to x squared. So, that's where this comes from, right? So then, we come to here, say, okay, yeah, let's multiply x by 2. Multiply by 1/2 out here, maintain equivalence. X to the fourth is just x to the squared squared. And now we can bring that simply down to u squared. Perfect. Now we've got 1/2 of 1/4 plus u squared, right? Perfect. The whole thinking is, this looks almost like, the antiderivative, this looks almost like, the derivative of arctan, but not quite. How do I get it there? How do I get closer to what I want, right? Bring that x to the fourth down to x squared. So now we come down to here, right? This is what we have, but it's still not the derivative of arctan, right? Still not quite what we want, right? Because that has to be 1 plus u squared. So what do we do about that? Well, now what I want to emphasize, what I do now is I use this identity. This is a very handy identity. After solving this, I of course looked at Symbolab's solution. Symbolab's solution is basically identical to mine, only Symbolab kind of messes around with a V substitution. I just use this identity. To get set up with that identity, you see what I do, right? I multiply by 1/1/4. So now we can have 1 plus, a constant times u squared. Multiply by that out there to maintain equivalence. So we keep going here. We've got this. We just simply use the identity and boom, we've got it. We've got the answer. Put x squared back into u. 1/4 of arctan, x squared over 2 plus c. Awesome. I want to show another way to go here. There's another identity that we could have used as well. And it really goes to show the more of these identities we know, the more and more useful they can be. Another thing we could have done here is use this identity. Okay, here's another identity we could have used. A over a squared plus x squared equals the arctan of x over a, right? And this is all ultimately due to the logic of a right angle triangle and Pythagoras' theorem. But anyways, we go back here. How would we apply that identity? Well, if we wanted to apply that, we'd be going down a different road, right? What I'd be doing instead is, putting a 2 up there, right? Multiply by 1/2 out here actually to maintain equivalence. Now we're perfectly set up, right? A is 2, right? We're perfectly set up. And now from here, it works out a little bit differently. Now we don't have 1/8 there, that's going to be 1/4. But really, this doesn't matter anymore, right? That's out of the picture. That doesn't matter at all. And we're really going to skip all the way down to here. Really, what's going to happen is we're going to skip all the way down to here. So I would say that identity is even more efficient in this case. All of those steps can be skipped, and that's another identity we can use. So huge takeaway. There's a lot of identities related to derivatives and inverse trig functions. They can come in handy and they're good to keep in mind.